In all of the problems of the last three videos, we were working with first-order systems, meaning we only had systems with first derivatives and nothing higher than that. What if we do want to work with higher derivatives, though? For example, what if we had a system that looked like y double prime is some matrix times y plus some matrix times y prime. So here we have the second derivative related to the functions and their first derivatives. If we were to write this out, maybe it'd be something like y1 double prime is a11 y1 through a1n yn, but then we also have b11 y1 prime through b1n yn prime. And then we have a whole bunch of these equations. Yn double prime is yn1 y1 through ann yn plus bn1 y1 prime through bnn yn prime. So all the second derivatives of the y's are related to both the y's and the y primes. This is what we call a second order system. Second order differential equations. We could go higher still. We could have a y triple prime that is related to the y's, y primes, and y double primes, and so on and so forth. But the process will be very similar, and I don't want to make it too much more complicated than we need to right now. Once we know how to turn this one into something we can solve, we should be able to understand how to turn other ones into ones we can solve. And plus, second order differential equations are very important and very useful. Third order and higher tend to not come up as often. So second order is probably the limit of what we really want to be working with, at least in this course. Now, of course, we don't want to make up a brand new process for this. We'd rather just change it into the process that we talked about in the other videos. So how do we do that? Well, what we're going to do is introduce more functions. We already have y1 through yn, but now we're going to invent new functions yn plus 1 through y2n. So we're going to have n more functions. These aren't going to be brand new functions. In fact, these functions, actually I'm going to go ahead and treat this as a column of new functions, but these functions are going to be the derivatives of the ones we already have. So yn plus 1 is going to be the derivative of y1. y2n is going to be the derivative of yn, and then all the ones in between are the derivatives of everything between y1 and yn. What does this mean? That means that we have a new system. We have a system where y1 prime is yn plus 1 through yn prime is y2n. So we express the derivatives of y1 through yn in terms of functions from y1 to y2n. And then we also have yn plus 1 prime. Well, that's the derivative of yn plus 1, but yn plus 1 is the derivative of y1. So this is actually the second derivative of y1. Second derivative of y1 is this thing. And then we keep going all the way to y2n prime. This is, again, y2n is yn prime, so y2n prime is yn double prime. So the derivative of that is then all that stuff. So now we actually do have a first order system in the 2n variables, or 2n functions, y1 through y2n. So we have a first order system that is twice the size of the original second order system that we started with. Of course, if we did a third order system, we'd do exactly the same thing. There we would have new functions for both y1 prime and y1 double prime, and so on and so forth for the other ones. That would mean that we'd have a new first order system that has triple the size of this one, of the original third order system. So potentially a lot of work, because we're going to end up with very big matrices that we're going to be working with, that we're going to be trying to find eigenvalues for. But solving these second order systems and third order systems is already inherently a lot of work, even if we're doing it by some other method. So this is actually not as bad as it possibly could have been. And in fact, these matrices, if we took the matrix for this one, it's always going to look something like, we're going to have, if we treat it as a block matrix, we're always going to have a bunch of zeros up in this part. Because we have all the, we just have 1 times each of these as we go, we're going to have 1s along the diagonal and zeros everywhere else. We actually have an identity matrix here. We're going to have the original A that we had from here in this spot. Actually, yeah, I didn't modify that, did I? So this, I said this is a first order system, but keep in mind this y1 prime is actually yn plus 1. And same thing for all these. These are, so this is n plus 1 through 2n and 2n. So yeah, should have modified that before. But basically all these that we have over here turn into the yn plus 1 through y2n, and so we have the matrix A here, and we have the matrix B here. So we can actually use the matrices that we were working with here, a matrix of all zeros, and the identity matrix. Those make up the matrix that we're going to be working with. And of course, having a bunch of zeros will actually make doing the eigenvalues not as bad as it might have otherwise have seemed to be. So let's actually put that into practice. Here is problem 6. It's an initial value problem, but it's second order. You're going to be doing similar problems in problem 5, but those are not going to be initial value problems. You'll just be looking for a general solution, and so you won't have the extra step of applying the initial values. But one thing to note here, when you actually have a second order system, and you're doing an initial value problem, you do actually need information about where the first derivatives start. This is actually going to be equivalent to when we actually introduce a y3 and a y4. These will actually just be the initial values of those y3 and y4. So keep in mind here we are saying that y3 is y1 prime and y4 is y2 prime. And then these equations here become y3 prime is equal to negative 2y2 plus y3 plus 2y4. And then y4 prime is equal to 2y1 plus 2y3 minus y4. And these 4 equations here are now our new system. Make a little bit more sense if we made this y1 prime is equal to y3, and same thing with y2 prime. But this is a new system, and that means we have an equation, or we have a matrix here, where our first one comes from y1 prime. It's going to be 0, 0, 1, 1, 0, 0, 1, 0, because the only one that we have here is a y3, and then we have a 0, y1, and so on and so forth. Then for y2 prime, we have 0, 0, 0, 1. y3 is going to be give us negative 2, 0, 1, 2. And then y4 is going to, sorry, this is y2. That negative 2 should be in the second slot. So, sorry, 0, negative 2, 1, 2. And then we have 2, 0, 2, negative 1. And this is the matrix we're going to find eigenvalues for, and we're going to find the eigenvectors for. So 4x4 matrix, we can do it, but just even a 2x2 system, when it comes to a second order system, gets a lot bigger. So we're not going to go any further than that. 3 by 3 system, we're going to be working with 6 by 6 matrices, and that is a little further than we ever want to go with it. But remember, we are going to actually need to look for eigenvalues. So we're going to take our diagonal elements minus lambda. Everything else stays the same. We work this out. Using the fact that we have a lot of zeros up here, this isn't as bad as it might seem. But ultimately, when we actually work it all out, and I'm going to skip all these steps. Remember, I just expanded along this first row, which means I have negative lambda times this 3 by 3, then plus 1 times 3 by 3 leaving out this second column, or sorry, third column. And it is quite a bit of calculational work, but eventually you get down to lambda to the fourth power minus lambda, or sorry, minus 5 times lambda squared plus 4. So, kind of a nice actual result here because we don't have any cubes or linear terms. And this also means that we can treat this as a quadratic in lambda squared, which actually means that we can factor this thing. We get lambda squared minus 1 times lambda squared minus 4. And then these are both factorable. So you have lambda minus 1 times lambda plus 1, and lambda minus 2 times lambda plus 2. So, a lot of work, but it's possible. So, now we get to go through each one of these 4 eigenvalues of 1, negative 1, 2, and negative 2, and find eigenvectors for them. So, might not be able to fit that all on one page. I'll try to get the first 2 at least. So, our first eigenvalue is 1. We go ahead and subtract 1 to each of our rows, or sorry, each of our diagonal elements. We have negative 1, negative 1, 0, negative 2. Everything else is the same. I am getting off track here. It's negative 2, 0, 2. Okay. Now we go through some row operations. In fact, our first 2 rows are very nice for us. So we can multiply those by negative 1. And then we get to fiddle with the other ones. It turns out this third row can go away, but our last row actually kind of sticks around. We'll get what? We'll have a row of all zeros at the bottom. And then for our third row, we'll have 2 zeros, followed by 2 and negative 1. That means we can get an x1. So I didn't quite get this to reduced row echelon form, but I got it to where we can actually read it off. So first of all, with this 2 here, I do want to pick a 2 for our fourth variable instead of a 1. But that means that once I use 2 there, then our third variable is going to be 1. Our fourth variable being 2 means our second variable is going to be 2. And then our third variable being 1 from this row means our first variable is going to be 1. So 1, 2, 1, 2 is the eigenvector corresponding to lambda 1. Lambda 2, I'm going to say this one's the negative 1. Do the same kind of thing. Try to get them a little bit better lined up this time. So now we're subtracting negative 1 from 1, so this becomes a 2. And then negative 1 minus negative 1 is a 0. Okay. Again, we can go ahead and keep that first row. In fact, keep the second row. We don't even have to multiplying by -1 this time. Then we use those to change the other ones. We'll get a row of all zeros at the bottom, and then here we'll end up with 1, 2. So again, not quite reduced row echelon form, but close enough. Here we don't have to multiply. We don't have to put 2 in the last slot. We'll just put a 1, which will make our third variable -2. Our second variable is going to be -1, and our first variable, again, since we have -2 here, we'll have a +2 for that one. So that's going to be our x2. Now lambda 3, this is going to be our 2. We subtract 2 from each of our diagonal elements. So we have a -2 there. We saw these ones are the same. We have a 0, -2, and then these are going to be the same as well. Sorry. This will be a 1, 0. This will become a -1 and 2. And 0, 1. This was still a 2, and then we have a -3. Keeping track of all this is maybe a little complicated, but that's what we have to do. Go ahead and multiply this first and second row by -1. I'm not going to divide them by 2, just leave the 2's as they are. We will again get a row of all zeros, and then here we're going to get a 1, -1. That means we get an x3. We can go ahead and pick 1, or actually because we have these 2's here, let's go ahead and pick 2. But then our third variable is going to have to be the same thing, so it's going to be a 2. Our second variable is going to be a 1. And then because our third variable is 2, our first variable is also going to be 1. So we have 1, 1, 2, 2. Finally, our last eigenvalue is -2. So we have 2's here. These are going to be the same thing. And then what are these? These are 3 and 1. Again, just going to keep those first 2 rows. We're going to get a row of all zeros, as we expect to. Those will be, we can turn those into zeros, and finally, those will turn into 1, 1. Again, you should probably go ahead and verify that this works. Go through some of the row operations for yourself. But I'm going to, again, pick 2 here, which will end up giving us a -2 here, a -1 here, and a 1 here. But we've done this enough times that I expect you to be able to do that. So, what is our y? Remember, we're going to take c1 times e to the lambda t times x1. So we have c1. Our first lambda is 1, so we have e to the t. Our first eigenvector was 1, 2, 1, 2. We have c2, e to our second lambda was -1. Our second eigenvector was 2, -1, -2, 1. We have c3, e to our our third eigenvalue was 2, so 2t. Our third eigenvector was 1, 1, 2, 2. And then we have c4, e to our fourth eigenvalue is -2, so -2t. And our fourth eigenvector is 1, -1, -2, 2. Of course, this is an initial value problem, so we're going to go ahead and actually let's I guess I've been putting this as a, so we don't have to put this into one single column. Let's go ahead and just plug in 0 right now. So we plug in 0. Obviously, all the e's become 1s, so we just have c1 times 1, 2, 1, 2, plus c2, 2, negative 1, negative 2, 1, plus c3, 1, 1, 2, 2, plus c4, 1, negative 1, negative 2, 2. And what is that supposed to equal? Well, remember, the first thing is supposed to be y1 of 0. Second one is supposed to be y2 of 0. Then we have y3 of 0, but remember, y3 is y1 prime. So y3 of 0 is this negative 3. So we have 1, 0, negative 3, and then again, y4 of 0 is y2 prime of 0, which is 2. So 1, 0, negative 3, 2. That's our column vector that we're supposed to get. 1, 0, negative 3, 2. And we're just solving for the c's. This is a linear system, and we'll go ahead and actually set this up as an augmented matrix. Alright, so we end up with this thing. The augmented part of 1, 0, negative 3, 2. And then we get to go through all the process of solving this. So I'll keep that first row. I'll change all these to zeros. When I did that, I got negative 5, negative 4, negative 3, negative 1, negative 3. Actually, you need a little bit more space here, so I'm going to move these over a little bit. And then we have negative 2, negative 4 here, a 1, negative 3, and something really nice here happens. We have a 0, 0, 0. That actually is going to save us a lot of time, the fact that we got that very nice one. I'm going to move that to my second row, and I'm going to divide it by negative 3. So I'm going to put that in here. So we have 1, 2, actually I'm going to, in the next step, I'm going to try to change that to a 0. So let's leave it as 0 for now. We're going to have this row. The only thing left there is the 1 in that spot, and we're going to use that 1 to cancel out everything else in that column. And in that first row, once we modify that 2, we'll be left with a 1, 1, 1. Then here we're going to have a negative 1, negative 3, negative 2. And we have a 1, negative 3, negative 4. Of course, I'm going to go ahead and use that fourth row as my new third row and use it to cancel out everything in that third column. So we'll have a 1, 0, 0 here. We'll still have this entire row is unchanged. Well, 0, 1, sorry, that should be another 0. 1, negative 3, and negative 4. We'll have a 0 there. And we'll be left with a negative 6, 6 as our last row. We'll have a negative 2, negative 2, negative 1 here. And our very last step, of course, everything came out very nice on that last row. We can go ahead and divide it by negative 6 to get a 1 here. We'll go ahead and use that 1 to cancel out the other stuff in that row, that column. So we'll get a nice identity matrix over here, and over here we saw the 0 there, and we get a 1 and a negative 1 for those there. So very nice constants, kind of probably designed that way. But we got to go ahead and plug those into our y. So remember, our y from before was this thing here. C2 is going to be 0, but C1, C4 are both 1, and C3 is negative 1. So we end up with an e to the t times our first eigenvalue, our first eigenvector, which is 1, 2, 1, 2. we have a minus e to the 2t times our third eigenvector of 1, 1, 2, 2. And then we have plus e to the negative 2t times our fourth eigenvector of 1, negative 1, negative 2, 2. Or in other words, if we write this all out, we have e to the t. Actually, let's write it out as our functions. Our y1, or y1 of, you can write that as a function, y1 of t is e to the t times 1 minus e to the 2t times 1 plus 1 times e to the negative 2t. y2 of t is 2 e to the t minus 1 times e to the 2t, then plus, or, well, negative e to the minus 2t. And if you want, you could write out y3 and y4. y3 would be e to the t minus 2 e to the 2t minus 2 e to the negative 2t. y4 would be 2 e to the t minus 2 e to the 2t plus 2 e to the negative 2t. But remember what y3 and y4 are. They're supposed to just be the derivatives of y1 and y2. And so if we're actually trying to solve this equation, the system of differential equations, we don't really need to write those out. It would be a good idea to verify, just to make sure that we didn't do anything wrong, that the derivatives of these are those y3 and y4. But we can actually show that. So if we differentiate this one, what happens? We have e to the t, which is what we expect here. We have minus 2 e to the 2t. That's what we get here with this 2. And then we have, bring that in that negative 2, we have minus 2 e to the negative 2t. And so we get a minus 2 times e to the negative 2t. And same thing for y2. Though our y4 is going to be the derivative of that. So this is our solution. That's our solution to that system. And that's all we need to do. Obviously, a lot of work. It's a long process, but that's all we need to do. It's very straightforward as long as we actually do, we get lucky at least, and actually do have 4 different eigenvectors that are linear independent. If we actually have 4 different eigenvalues, and that's what makes that guaranteed. If we had any repeated eigenvalues, we might not have that happen. That's what we need to actually talk a little bit about in section 6.3, even though that's not going to be the main focus of that section. So we're going to come back to this a little bit, but we're mostly done with it. So, fun stuff. A little crash course in differential equations. So, again, you have homework on this. I am not going to ask you any questions about this on the exam, just because it is a long process, and it's a lot of work. But hopefully it gives you an appreciation of how all this stuff about, say, eigenvalues specifically, but even more generally stuff about linear equations can become very relevant to problems where it didn't seem otherwise relevant. So, see you again in the next video for our last section, section 6.3, where we do a little bit more with eigenvalues. So, see ya.